Hey guys, welcome. Yeah, so problem 4 here, and in part A, we have to use L'Hopital's rule, and part B is a convergence question. So here's part A, which is to show using L'Hopital's rule that this limit is equal to 1. Now, I already made several videos on L'Hopital's rule, so check those out. But yeah, this will be another example on L'Hopital's. And remember that there are many indeterminate forms that trigger L'Hopital's rule, but in order for us to actually apply it, we need to get to the indeterminate forms 0 over 0 or infinity over infinity. So in order to do that in this situation, we need to exploit this little property of the natural log in e, which is that e to the natural log of anything is going to give us back anything. That's to say that because e and ln are inverses, they cancel, so to speak. All right. So using this little property, then we could write the original question here in this way. And all I've done here in the middle is just exploited this little interplay between e and ln. Now, in the exponent of e, I can apply the properties of logs, in particular the property of the natural log here, and write this 1 over n in front of ln, right? And so that's what I've displayed here in this last step. And from there, we could go like this. And what I've done now is two things. One is I've noticed that 1 over n times ln of n is just ln of n over n. And then this limit is n goes to infinity. I can write in the exponent. And that's a property of limits, which is that like if you have the limit as x goes to a of f of g of x, you could write f of the limit is x goes to a of g of x. And that's what I've done. Okay, cool. So then, here in this final step, if we actually find the limit as n goes to infinity, we get ln of infinity over infinity, which is like infinity over infinity, right? So we get the desired indeterminate form that tells us that we can use L'Hopital's rule. And so since we have infinity over infinity, what L'Hopital's rule would say is that we could take the limit as n goes to infinity of the quotient made of the derivative of the numerator divided by the derivative of the denominator. Not the quotient rule for derivatives, but just the derivative of the numerator by itself, and then the derivative of the denominator by itself, and then take that quotient and send n to infinity, and it will be the same as finding the limit as n goes to infinity of ln of n over n. So if we do just that, which is take the derivative of the numerator and the denominator, we see that the derivative of ln of n is 1 over n, and the derivative of this denominator n here is just 1. So in the exponent of e, we'll have limit as n goes to infinity of 1 over n over 1, which is same as limit as n goes to infinity of just 1 over n. And that clearly is 0 when n goes to infinity, 1 over n goes to 0. So we have e to the 0, which is 1 as desired. All right, cool. So let's go to part B. And here is part B. It says determine whether or not the following series converges. And the series we're dealing with is this. So let's look at what we're given inside of sigma in this series. So let's look at Bn and manipulate it a little to get a better feel for it. Notice that Bn, using exponent rules in the denominator, can be written in this middle way, right? And I have in this third step just like gotten rid of the 1 on n, because that's just n, right? Otherwise, now looking at this final rewriting of Bn, we see that like 1 over n is a nice other series to compare it to. And we're not going to do a direct comparison, but rather we're going to do a limit comparison. So we're going to say the limit of an over bn, where an is 1 over n, and we know that 1 over n diverges. That's the harmonic series. And so that's what we're going to do. So taking an to be 1 over n and using the limit comparison test, we can consider this quotient an over bn as n goes to infinity, which is going to be 1 over n divided by the bn that we have rewritten in this final form here. And then what we're going to be able to do is cancel a 1 over n here in this numerator, the blue one, and then a 1 over n in the denominator, so that we could write this following guy, right? And now we have like a cumbersome fraction, but we could just rewrite it like this, right? But wait, by part A, we knew that this limit is equal to 1, right? And so since the limit is n goes to infinity of an over bn is equal to 1, which is less than infinity but greater than 0, we know that either both the series involving an and bn diverge or they both converge. Since we know that an, which is 1 over n, diverges, we conclude that bn, the given series, also diverges by the limit comparison test. Yeah? Okay, cool. So that's it, and this is it for problem 4, but 4 more to go. Keep watching. Take care.